Welcome to lesson 2.3 in the electronics lecture series. In this lesson, we're going to be talking about op amps. We're going to take another way of analyzing op amps. We're going to look at them as a feedback amplifier. So what's the point of this lecture? There is a huge body of math and engineering around control systems, particularly control systems that incorporate feedback into their controllers. So controllers with feedback are a huge existing issue. There's several, you can find textbooks anywhere that have, voluminous collection of equations relating to these, techniques you can use for improving them, ways of examining non-ideal effects as they propagate through these sorts of networks. So rather than basically taking every single circuit we encounter and analyzing everything about it from scratch, we're going to start to look at op amps as a standard feedback amplifier, and we're going to build a collection of equations for those standard feedback amplifiers. And then when we encounter some novel op amp in the wild, we're going to analyze the op amp in order to find its feedback model and then just use all those equations that we already have. So this video is basically going over that background on the going over that background on the standard feedback amplifier model. And you can see the feedback amplifier is fairly straightforward. It is a forward path gain. So wires in this case represent signals, blocks represent functions. In this case, these are gain functions, these blocks here. This is a summing junction, which you can see there's a plus sign and a minus sign, which means it's summing the negative, which we also call summing the negative subtraction. So what we have is as the signal moves through this signal gets amplified by this forward path gain, this open loop gain, and then it goes to the output. But part of that output, or that output signal, I should say, not part of it, that output signal also travels through a feedback network, and it gets amplified by that feedback network. And when I say amplified, normally these actually attenuate, which is just a special type of amplification with a gain of less than 1. And then that amplified signal goes into this summing junction, which is going to take the input signal, subtract this signal that comes through this feedback network, and the difference is what gets fed on to continue the process, right? It's what gets fed on through that forward loop. So this topology is fairly easy to understand. You just have a signal that gets amplified going forward. It gets amplified going backwards, and the difference is taken between an input and that feedback network signal. But as we'll see, it's fairly straightforward. The equations aren't necessarily intuitive, though, looking at this. So let's jump right into the equations. So again, these are all equations. If you take control systems, you're going to see these equations a million times. These equations are the basis for most control system analysis. And if you're interested in this, you can look up videos on control systems. They're really neat. If you go through our curriculum, you'll definitely get that. But in terms of understanding how complicated electronic systems, interconnected electronic systems, especially electronic systems that interface with the real world, in terms of looking at how they're modeled and tuned and improved, control systems is everything. It's really important. It's really good to know. Okay, so looking again, this what's here is exactly what we had in the last slide, basically just a little more symbolic, right? So basically we have a forward path amplification, a feedback path amplification, and a summing junction. And then we have an input and output, right? Source and load, input, output. Now, it's important to be clear with terminology here. We want to, right off the bat, define, we create a bunch of variables here. Let's give the names for those variables. So first of all, that is the input signal. Xi is the input signal. XO is the output signal. XF is the feedback signal. X epsilon here, that is the error signal. So basically the input minus the feedback signal gives you the error. We call it the error term here. And then we have the names for these different things. We have the open loop gain, and we have the feedback factor. So that's so A and B. A is the forward path open loop gain. B is the feedback path feedback factor, which is just a gain term. Now, I want to be clear, we have to be very careful with this term open loop gain because, and this is a really, really, really important concept to understand. When we initially talked about op amps, we were talking about the amplifier itself. So we were talking about basically, you know, the symbol, the triangle symbol op amp. And when we're talking about the triangle symbol op amp, the open loop gain is a parameter of that physical op amp device. What we're talking about though moving forward is not just a bare op amp. We're talking about one of the neat things about op amps is you can add a bunch of external resistors to op amps to make all kinds of different flavors of amplifiers. You can make current to voltage amplifiers. You can make current to current amplifiers. So even though a standard op amp is a voltage to voltage amplifier, you can, by connecting this op amp to this external network of resistors and sometimes capacitors and inductors, you can create different types of amplifiers. So when we talk about open loop gain here, we are talking about the open loop gain of the whole thingamajig, not just the op amp itself. We're talking about the open loop gain of the entire op amp system. So if you had a resistor divider at the input, and then the op amp, and then you had a voltage output, and it was converted to a current, you're going to manipulate these signals a lot, and it's very possible that the forward gain of your op amp is not the same as the actual open loop gain of the op amp itself. So really important thing, the open loop gain of the op amp is not necessarily equal to the open loop gain of your feedback amplifier system. So but to make it even more confusing, sometimes it is the same. So in certain op amp configurations, they will be the same, but in other op amp configurations, they're not the same. So it's just really important to note, we talk about open loop gain both for the physical op amp itself, and we talk about open loop gain for the system that we create that has an op amp at its core. And they're two different things, and they're not always equal to each other. Okay, with that out of the way, let's start just working through some of the math for this thing. I got to clean up some of my mess here. Let's start working through the math here. So first of all, we're just going to start piecing together the equations that we know. That's fairly straightforward. This output signal is just the input, the error signal times this amplification stage. I mean, that's what an amplifier is. So output is the open loop gain times this error signal. Okay. Next thing is the feedback signal is going to be the output times this feedback factor times this feedback gain, which again, that also makes sense because we have our output signal, it goes through this gain B and it comes out as that feedback signal. So it's, of course, feedback signal is just going to be the output times whatever that gain B was. Okay. And partially these equations are not intuitive, but the pieces of them are. So sometimes you have to put together the pieces and then do a little math, and then you're left with an equation that might not make sense intuitively, but it, you know, the pieces made sense intuitively, and the math was something you understood, so you believe that it's true. So, and then we have the error term is equal to the input signal, the error signal is equal to the input signal minus the feedback signal. And that makes sense. All we're doing, I mean, that's just what this summing junction is doing. So that makes sense. One thing to note, where else have we looked at sort of at the input to an amplifier, we say we take the difference between two signals at the input of an amplifier. Well, that's kind of what an op amp is doing, right? We have VP and VN, and the difference between them is what gets amplified. So that's just that's ultimately those are the same things, but for now we're just treating them as two separate signals that are producing an error that's being amplified. So that is ultimately the same thing, and we'll come back to that. But for now, we're just going to stick with just the standard sort of error signal production equation here. Okay, so now here's the interesting part. Now we get to this expression, the expression for the overall gain of this system. So gain of this system, how do we get to this expression? Well, let's take this equation and let's plug this in here. So let's say you with me now? Okay. And then let's also take this error signal. So we know from this equation here that the error is going to be that. So let's plug that in here. And then we're left with okay, so far so good. Let's separate XO and XI. So let's do, so we're going to move this to the other side of the equation. So we're going to say, okay, I'm going to make myself some space here because I don't want to write over my face. I do that sometimes. Sometimes I write, you know, on my screen, the preview of the video of me isn't quite in the same spot all the time. So sometimes I write behind my face. I'm sorry if I do that. So we're just going to start to move this work over on this part of the page here. So what I'm going to do now is I'm going to factor out this XO here. So I'm just going to say XO times 1 over A epsilon plus B equals XI. And then we will just get this ratio. So we want to find this ratio of the output signal to the input signal, which is the gain for our overall system. So let's reshuffle it. Let's divide both sides by XI. Let's also divide both sides by this thing here. Well, I'll redraw it now. So dividing both sides by that, we get so taking that expression, and I don't like that fraction in the denominator, so I'm going to multiply this by A epsilon over A epsilon. And what we get is A epsilon over 1 plus A epsilon B. Oh, look at that. All right, so we got back to our expression. This is the feedback equation. This is so important. So the feedback equation is basically saying in a topology with feedback, in a system like this, where you produce an error, amplify it, and then feed it back through a feedback network, the overall gain of these systems is given by this expression here. Let's look at that expression. So that expression, it doesn't look like much right now. A epsilon divided by 1 plus A epsilon times B. But what happens when A epsilon gets very, very, very large? When A epsilon gets very large, when we have a very high gain here, this expression tends towards, the gain tends towards 1 over B. This is really cool. So basically, by dictating the feedback network, we could generate a gain that is the inverse of the feedback. And it makes sense when you think about these, because basically what's happening is you're taking a signal, this output, and you're only feeding back a piece of it. So you're feeding back some piece of it. So let's say you're feeding back 1/50th. Let's say you're feeding back 1/50 of this output back to this input here. Well, then what's going to happen is if there's any error, that error is going to get amplified until this output is so big that 1/50th of this output cancels out this source. So by only feeding back a 50th of the signal, you're forcing the system to produce a gain of 50 to cancel out that difference between the input and the output. Oh, it's very powerful. This is a very powerful tool. This is ultimately what allows us to create things like op amps. It's extremely useful. It is, again, the cornerstone of control systems. That's the background on it. So this equation right here, super important. So this equation right here, the feedback equation, if you only get to memorize one equation this year, make it this one. This one is a big one. Now and forever, the feedback equation is fantastic. So, okay. So now that we have this expression, let's look at some other things. So let's look at some other features of this. We've kind of defined this sort of generic case feedback amplifier network. Now let's sort of start piecing together some other terminology here. One piece of terminology that we look at that's very useful to look at is the loop gain. The loop gain basically refers to the total gain that a signal gets as it passes through this loop, right? So as a signal passes all the way through this loop, what's the total gain that it experiences? Well, it's fairly obvious. The total gain that it experiences is A epsilon here, the open loop gain, times this feedback, sort of the gain in the feedback network. And then also it enters in the negative side of a summing amplifier, which means we're basically adding the negative. So we're negating the signal and then adding that. So we also get the negation here. Well, we have a term that we call loop gain. Loop gain is the negated version of that. So we're taking away the negative sign. So the loop gain is basically, it is this forward open loop gain times this backward feedback factor. And this is a really convenient term, especially for keeping equations clean. So basically, once we've identified this loop gain, there's a lot of things that we can describe just using this loop gain. So among them, let's take that equation that we just produced, the feedback equation, and rewrite it using this loop gain term. Well, we can rewrite this as this. And as we talked about in the last slide, as the gain of our network, as the open loop gain tends towards infinity, or as the gain tends towards infinity, the overall gain of this feedback amplifier network tends towards 1 over that feedback ratio. And you can see it very clearly here. So basically, as this loop gain tends towards infinity, this term tends towards 1, and the overall gain tends towards 1 over b. The other thing we can say is, how does the gain deviate from the ideal? We can say the actual gain of the network is the ideal gain times 1 over 1 plus 1 over the loop gain. And this is, the book goes through the derivation of these equations. I'll derive some of these equations when it's helpful. Like this, I think the deriving the feedback equation is important, but the book didn't. The book doesn't have the derivation of that, but this one, you can take it as a given. It's not that much math to go through it. So this is a really good way to basically see how much is your gain going to deviate from the ideal. And all you need to know how much the gain deviates from the ideal is the loop gain. And this is why, as I mentioned earlier, once we establish these standard case equations, all we have to do when we have any op-amp circuit in the future is, for that particular op-amp configuration, calculate the loop gain, and then we can immediately see how much the gain deviates from ideal. Very powerful to generate these sorts of equations. Here's another way of writing that. So this is the same equation, just written a slightly different way. And then we have this gain error here. So this is basically just looking at the kind of percentage deviation from ideal your system has. One thing to note, this equation right here is directly from the book Franco 4th edition, and it leaves off this 100. So if you want a percentage, and I don't personally like percentages. I don't like percentages in general. I don't know why we need things to be between 0 and 100. I don't know. But maybe Franco doesn't either. That's why he left it out. That's why he left it out of the equation. But just know, if you're looking at the book, that equation's wrong. It needs to have that 100 there. If you actually want gain error percentage. I think it's gain error. Maybe it's gain efficiency. I don't know. I can't remember the exact acronym. Basically, though, it just tells you what portion of your what fractional percentage of your ideal gain you'll have due to non-ideal effects. And again, very powerful, right? You know, if in this case, if L went to, sorry, it's what percentage of your what percentage deviation from your ideal gain you have. So as L tends towards infinity, this term tends towards 0, and you start to get to 0% error. So it must be error. Having a little mental slip here. Yeah, so very, very useful equations here. All right, let's do an example. So what loop gain is needed to achieve a gain error of less than 1% or a gain error of less than 0.01%. So this is basically if we're creating an amplifier and we're okay with a 1% error, then what's our overall loop gain that's acceptable? So going back to this expression here, the loop gain percentage is 100 times 1 over 1 plus, I messed it all up, can't see it. So loop gain is 100 times 1 over 1 plus L. So let's just do 100 times 1 over 1 plus L. Is that it? Okay, so now if we want this to be less than 1%, so this has to be less than or equal to 1. So just doing a little bit of math here, right? We're going to have, let's see. So L plus 1 it's got to be less than or equal to 1 over, 100. Oh, I did it. I inverted it. So we got to switch it. Sorry. Going back to middle school here. Okay, so so L has to be greater than or equal to 99. Is that right? Let's just really quickly sanity check myself here. Fast forward if you trust me here. So, oh yeah, what am I doing? Yeah. So obviously 99 plus 1 is 100. 100 divided by 100 is 1. Okay, perfect. So loop gain's got to be greater than or equal to 99 to have a gain error of less than 1%, less than or equal to 1%. Now let's do gain error less than or equal to 0.01%. So we say 100 times 1 over 1 plus L less than or equal to 0.01%. So that is dividing both sides by 100. So we get 1 over 1 plus L less than or equal to 0.0. Just add a couple zeros here. Now we're going to invert this, but when we invert both sides of the equation, we have to switch that direction here. So 1 plus L greater than or equal to, what's that going to be? 10,000, right? So L has to be greater than or equal to 9,999. Cool. So look at that, right? If we want to have a feedback amplifier that has a gain error of less than 1%, all we need to have is a loop gain of 99 or greater. But if we want a gain error of less than 0.01%, it's got to be pretty much 10,000. So we have to have a loop gain of 10,000. Okay. Now again, though, loop gain, not the same as open loop gain. So loop gain is the open loop gain of the system, which is not necessarily the open loop gain of the amplifier itself, times that feedback gain. And remember, the feedback gain, in most op-amp circuits, that feedback network has a gain of much less than 1. So, in a gain of 50 op-amp, the feedback gain would be 1/50th. So if you're looking at this loop gain and you're like, oh, we just have to have a loop gain of 10,000 to get this kind of error as less than 0.01%. That's the loop gain. So as you'll see, that means you'd probably need if your circuit is actually amplifying the signal, you would actually need an open loop gain that was higher than that to achieve that. So okay. So we now have sort of put together this model for a feedback, sort of this ideal or non-ideal feedback amplifier topology. We've generated a set of equations for it. Now let's tie it into the op-amp. I kind of just mentioned something that tied it back into the op-amp, but let's look at, if we go back to our feedback model and incorporate loop gain into our feedback model, we can find that the error signal is the input signal divided by 1 plus L. So what happens as L goes to infinity? As the loop gain goes to infinity, this expression goes to 0. So what does the error going to 0 mean? How does that tie into our previous analysis of op-amps? Well, this is basically referring to that assumption that we make. The simplifying assumption we make with op-amps is that the potential difference between the positive and negative terminals is 0. That's basically what this is. That's this equation from the feedback model, as the loop gain tends towards infinity, shows us also that, yes, this error term will tend to 0, which is the same thing as saying Vp minus Vn equals 0 as our ideal assumption. And let's look at this feedback, right? So the feedback signal equals the input signal divided by 1 plus 1 over L. So let's look here. As L goes to infinity, what happens? As L goes to infinity, this term goes to 0, and we're left with equals xi. So basically, as L goes to infinity, the feedback signal equals the input signal. So the feedback signal will tend towards the input signal. This is basically saying the same thing. This is that Vp equals Vn. So our equation Vp equals Vn in the ideal op-amp case, that's expressed here in the limit as loop gain goes to infinity. One important parameter of knowing these things like the loop gain and the open loop gain and the feedback gain or the feedback ratio or whatever term you want to call it, the feedback A and B. I'm going to mix terms, so I'm just going to call it A and B. So one nice thing about finding these terms and looking at analyzing feedback amplifiers using these terms is you can very easily look at how the gain is affected by small changes in these parameters. So let's look, for instance, at how, if we go back to our feedback model, we can take the derivative of this with respect to the open loop gain AE. And if we do that, we find that the change in our gain is dictated by this expression here. So again, all we did is took that original equation, took the derivative with respect to A epsilon, which I just called AE, I think. I guess E and epsilon aren't the same thing, but close enough. And so what do we have? We see that we have this, again, we're multiplying everything by hundreds just because I guess we like percentages, but basically this is just saying the change in the ratio change in gain is proportional to the ratio change in the open loop gain attenuated by this coefficient here. So it is attenuated by this coefficient 1 over 1 plus L, which basically is saying as L gets very big, changes in the open loop gain have very little impact on changes in the overall gain. So that's very important that basically this loop gain, this topology, desensitizes the overall amplification to changes in the open loop gain. So changes in the forward gain. And you kind of know this from what we've talked about op amps in the past, where we say an op amp will still kind of work as long as it has a very big forward gain, open loop gain. It doesn't have to have infinite, which is our ideal assumption. It just have a very big open loop gain. And that's basically what this is saying, right? It's just, if it's a big open loop gain, and we're probably going to have a fairly big loop gain, and so it's going to be desensitized to these changes. It's going to be, small changes don't really have a big impact. The same is not true for the feedback ratio. The same is not true for that feedback gain, B. If we take this original equation and we take the derivative with respect to B, and we take the ratio of the change in gain versus the change in B, what do we see? 1 to 1. So we see a 1-to-1 change. If we have a 5% change in B, we have a 5% change in the overall gain. Where have you seen this before? Well, imagine we were making a non-inverting amplifier topology where you have the input connected to the positive terminal of the op amp, and you have a feedback network, a 2-resistor feedback network. What if one of those resistors was off by 5%? If one of those resistors was off by 5%, you're going to have a 5% error in your feedback network, which is going to produce a 5% error in your output magnitude, or approximately, right? And so you basically already know this. This is basically saying that error in the resistors that make up a feedback network is very important. It has a big impact on the overall behavior of the circuit. But error in the open loop gain of the op amp, as long as the open loop gain of the op amp is big, doesn't really matter so much. Let's do an actual question that relates to this. So let's say we have a circuit where the open loop gain is 10 to the 5th and B is 0.01. So this would be kind of like a gain of 100 amplifier, basically. Find the percentage change in gain due to a 10% change in A epsilon, or in the open loop gain, and compare that to the change due to a 10% change in B. Okay, so now we're only looking at the percentage change due to these terms. So, if you look at this equation, we have a percentage change due to the change in open loop gain, and a percentage change due to, and a ratio here due to the loop gain. And then here we just have this percentage change in B. So first of all, let's calculate the loop gain for this system. So what's the loop gain as described here? Well, the loop gain is going to be the forward gain. It's going to be that open loop gain times B. So that's going to be 10 to the 5th times 10 to the minus 2nd. That's going to be 10 to the 3rd. So our loop gain is 10 to the 3rd. So our first question is 10% change in A epsilon. So basically, I'm just going to replace this. This is basically just 10%. So oops. So we'll just call that a 10, play fast and loose with it a little bit. And then L, so basically this overall expression is going to be 1 over 1 plus L times 10. That's going to be 1 over 1 plus 10 to the 3rd times 10. That's going to be so I get 0.00999%. So that's, you might think that's 0.01. It's not actually. It's close though. It's close. I think the book sometimes just says that's close to 0.01. Because what happens is you get this 10 to the 3rd plus 1, right? Because you get this little change. So what do we get? So a 10% change, in this case, a 10% change in the open loop gain led to only a 0.01% change in the overall gain of the system. That's incredible, right? That is the power of op amps. That's the power of these feedback amplifier networks, is, you know, the precision of your amplifier isn't really that important. It's heavily desensitized by this feedback network. But let's look at B. 10% change in B, this term is 10%. The error is straight up 10%. So error in the feedback network is really important, critically important, one-to-one important. The overall error, the overall gain accuracy is only as accurate as the accuracy of your feedback network, which means if you need to have a precise gain, you better have precise resistors in practice, right? However, the open loop gain, heavily desensitized, right? Big difference. So now this is not 1%, right? This is 0.01%. So so we're talking a huge difference here. There's another feature of these sorts of analyzing these kinds of networks as feedback networks, and one of them is looking at noise desensitivity. So a lot of times amplifiers not only have non-infinite gain to them, but quite often amplifiers inject noise based on the type of amplifier. So, you know, some amplifiers inject hum, right? Some of them, part of the amplifier is operated at a certain frequency, and so they'll inject hum. Some of them will just pick up like line noise. Some of them will have these weird sorts of harmonics due to just resonant frequencies in the amplifier. So it's really important sometimes to look at, let's say you have an amplifier with feedback. How does noise impact the overall gain? And also, how does it matter where noise is injected in this system? So if we're thinking about an feedback amplifier topology where there is noise injected within the amplifier, usually it's good to sort of split the amplifier up into two amplifier stages with a noise injection in the middle. So this is the way of showing noise was inserted by the amplifier itself. So you had noise inside the circuit, noise produced by the circuitry inside the amplifier. And then we also have noise at the input. So that could be, you know, let's say you're amplifying a light signal, a signal that comes to an LED from light. You're going to have some noise at that input due to, you know, Brownian noise in the actual PN junction, just random sort of noise. You know, sometimes you'll have noise due to the limited number of actual photons that are striking it. You'll have all sorts of sources of noise at the input. And then at the output too, there's also noise at the output. So, or the output side of things. So that can be caused by a lot of stuff. That can be caused by, you know, noise picked up by a line. It can be caused by output resistance. It can be caused by all sorts of things. And then again, you have that noise in the middle. When we analyze this network, we see that the output is 1 over B times the input. That was sort of our ideal case that we looked at before, right? In these sorts of networks, ideally that's what you get, where you have, and again, this is as the loop gain goes to infinity. You get that the output is 1 over the feedback network gain times the input. But then we also have this, it's also 1 over B times that noise at the input. So that's an important thing, is that input noise to these systems, there's no way to get rid of it. I mean, there's no way to differentiate input noise with input. So input, what's the actual input you were looking for? What's input noise? There's no way for these systems to tell without additional design on your part. What does additional design mean? Well, you could filter things, right? If you know the signal you're looking at is going to be between 20 hertz and 20 kilohertz, like if the signal you're looking at is from a microphone, from a person talking, well, then you could filter. You could put a filter on the input. That could be one way to get rid of input noise. But other than that, there's no way to, other than knowing the characteristics of your input signal, there's no way to actually get rid of that noise at the input. However, one thing you'll see is that noise injected inside the amplifier stage is attenuated by the open loop gain. So it's attenuated by, I guess, the first half of the open loop gain. And noise at the output of this, noise at the output before it gets sampled as feedback and brought back, that's attenuated by both gain stages. Or, and again, the two stages of gain here are, we took a single amplifier, cut it in half, and showed the noise being injected in the middle. But it's still a very important concept. And that concept is these amplifier networks that use feedback, even cascaded amplifiers with feedback, are very insensitive to noise that was added in later stages of amplification. But they are very sensitive to noise at the input. So they can't do anything with noise at the input. But as noise gets added later on in the amplifier stage, it's easier and easier to get rid of using this feedback. What does that mean? Quite often when we work with power amplifiers, an amplifier that needs to produce, hundreds or thousands or millions of watts of power, usually they're terrible. They usually, these are not good amplifiers. They're designed for power. They're not designed for precision usually. So they're sloppy. They got lots of air. They got lots of noise. They're terrible. But if we incorporate them as the final stage of a feedback amplifier network, we can use feedback to clean up an enormous portion of that noise. So quite often, if we need a sensitive amplification, overall amplification, but the last stage of it needs to be a high-powered output stage, sometimes all we have to do is pull the output signal and have it be our feedback signal for this feedback amplifier topology, and we can do a huge amount to get rid of that noise. This is standard practice. Class D amplifiers, which we'll talk about later in this class, are notorious for having pretty bad noise. They pick up noise from places, they produce noise. However, there are ways you can clean that noise up by just simply taking the output after it's gone through those amplification stages, feeding it back as feedback to your overall amplifier design. And another thing to note, though, is the fact that we are sensitive to noise early on in this amplifier stage is a big reason why you'll see preamplifiers as a very important concept in engineering. Preamplifiers are basically this idea of before you mess with a signal, before you do things that might add noise to a signal, you want to give it a little bit of high precision, highly linear, low noise amplification right off the bat. So generally you would take an input signal, before you touch it, before you do anything that might add noise, sometimes you want to give it a little bit of gain with a very good, very expensive amplifier stage. That's usually what preamplifiers are. They're sort of that, give a good amplification early, add noise, add a terrible amplification later, and then give the whole thing feedback. So, okay. So that does it for the feedback model. So, so before I close this thing out, I guess I thought I was gonna have a last slide here. But that does it for this lecture for today, discussing the feedback model. What are we gonna do next time? So in the next lecture, what we're going to do is we're gonna take this feedback model and we're gonna say for any, we're gonna take the op-amp circuits we've looked at in the past and we're gonna say, let's take these op-amp circuits and represent them as a feedback model amplifier. So we're gonna take circuits that have an op-amp and have resistors and the feedback path, resistors at the input, resistors at the output, resistors that convert currents to voltages, resistors that convert voltages to currents. And we're going to calculate these parameters we talked about today. We're going to calculate the open loop gain for the system, not the open loop gain for the op-amp. We're going to calculate the feedback gain. We're going to calculate that B term. And we're going to calculate the loop gain after we've calculated those first two. So we're going to look at that analysis for different op-amp topologies in the next lecture. And then what you'll be able to do is, once you have those topologies and you've done that math once, you now have a really quick way of saying, okay, based on these equations for my A, my A epsilon, based on these equations for my B, all I need to do is plug in numbers and I can find all these other parameters really quickly. I can find my gain error, I can find my input impedance error, my output impedance error, find all these things very quickly to solve problems much faster in this class. But it's a different way of looking at op-amps, a different way of analyzing op-amps. A lot of times what confuses people about this book is we'll do an op-amp analysis one way, then we'll do it another way, then we'll do it another way. This is another way. The main thing to do is if you're given a problem in the book, you know, look at what section it's in and look at what info they give you. So if they give you information like, if they give you parameters that would allow you to do a feedback amplifier topology analysis, then they're probably asking you to do that, feedback amplifier topology analysis. Okay, I've talked too much. This video has gone on too long. Let's be done. Thanks for watching.